Hello everybody. Today we are going to be talking about how to get a basis for the column space of a matrix. All right, first thing we have to do is remember what the column space is. So it is the span of the columns of A. And remember, another way to think about that is the set of all linear combinations of those columns of A. All right, and we are trying to find a basis, and let's remember a basis has to be two things. We want a basis for column space of A. A basis has to span whatever set we're talking about, and it needs to be linearly independent. So because of the definition of column space, the columns of A are already a spanning set. Okay, so all of the columns of A are a spanning set for the column space of A. But we want to throw out the ones that are linearly dependent. So spanning set theorem says that we can throw out the dependent, or rather the redundant columns. Okay, throw out columns until we get a linearly independent set or subset of those columns. So we need to figure out which ones from the columns of A form a linearly independent set. So if you remember, how do we figure out linear independence and columns of a matrix? We're going to row reduce, okay? So we'll row reduce, right? And the pivot columns are the ones that are linearly independent. So we're going to row reduce and find the pivots, just like we do for lots of other things in linear algebra. But we have to think about first, how do row operations actually affect the column space? Okay, so let's just look at a quick example here. Okay, so 0. Let's not do 0. Actually, let's do like 3, 6. Okay, so the column space here. Okay, let's call this matrix A. Column spaces of A is going to be everything that's a linear combination of those two columns. So say C1 times 2, 3 plus C2 times 4, 6. Okay, C1 and C2 are in R. All right, but if we were to row reduce this, and let's call it a hat, if say we row reduce, we could divide the first row by 2 and get 1, and then 2, and then we could use that 1 to clear out the 3. Let's think about that for just a minute. So we would multiply this, -3 and -6. So then we would add it and we would get a row of zeros right here. So what this tells us, right, is that the original two columns were dependent, and we can see, right, 2 and 3, that's half of this column, 4 and 6. But if we look at the column space of a hat, okay, it would be C1 times 1, 0 plus C2 times 2, 0, where C1 and C2 are scalars in R. And we look and see those row operations told us where that pivot was and told us that we only need 1 for a linearly independent set. But it also tells us that the column space has changed, okay? So these two column spaces are not equal. For instance, 2, 3 is in this column space, but this one does not have 2, 3, right? Because 0 here and 0 here, we can never get that 3 in the second component. Okay, so row operations, row ops change the column space, but they preserve dependence relations on the columns. Okay, so what that means is that to get a basis for the column space of A, you're going to row reduce, and you only have to row reduce enough to find the pivots, because the pivots tell you which columns are independent and which columns are dependent. And then your basis is the pivot columns of your original matrix A. Okay, right? Because like in this example, this reduced echelon form matrix tells us that, right, free variable means that the columns are dependent, okay? So we just need the first one that has the pivot to have an independent set. But the span of those is different than the span of the original, and column space is span of the original. So figure out where the pivots are, go back to that column to get your basis. So in this example above, we found out pivot is in the first column, but we go back to the first column in the original matrix, so your basis would just be 2, 3. All right, and let's look at one more example. We want to find a basis for a column space of A, where A is our matrix here. Remember, this is a 3 by 4, and column space is always a subspace, right? You're adding all of these columns, these 3 component vectors, you're going to get a 3-component vector. It's always a subspace of Rm if your matrix is an m by n matrix. All right, if you watched the video about basis for a null space, this matrix should look familiar because it's the same one we were talking about there. So when we row reduce, I'm not going to do that computation. It's in the previous video about basis for a null space, but when we row reduce this, you get the following matrix. Okay. And we find out where the pivots are here, right? Here's a pivot. Here's a pivot. Those are the only 2 pivots. So what this tells us is that we need the original first column and the original second column from our matrix A. Okay. So a basis for the column space of A is going to be those original columns, 0, 1, -2. So there's our basis. And note, we don't just want these 2 columns over here, because all we can get, right, we could only get vectors with entries in the first 2 components. Because there's zeros here, we're never going to be able to get non-zero things. But the original columns, right, there's a bunch of non-zero stuff down here, so we need to be able to get non-zero stuff. So the row reduction does change the column space, but it does still tell you which ones are independent, okay? And if you'll notice, right, we had 2 pivots. So there was 2 vectors in basis of, whoops, not the null space, the column space. But we also saw there's 2 free variables, and in the last one, the last video, we talked about how the number of free variables corresponded to the number of vectors in your basis of the null space, right? And that worked with this example, but it is going to work in general. So in general, the number of pivots is your number of vectors in your basis for a column space. The number of free variables is the number of vectors in a basis for the null space. And that's it for right now.